Yeah, so how I got into Julia, I do research in DNA sequencing and RNA sequencing. So the thing that's been happening in molecular biology research in like the last 5 years is that sequencing has become really cheap. So like a lot of assays and technologies have been replaced by sequencing, which is great, except that we're going from data sets that are like 1 megabyte of tables to data sets that are like hundreds of gigabytes of these giant sequencing text files. So I think there's a desperate need for a programming language that's usable by non-experts but capable of generating fast code. Since a lot of people in bioinformatics are, biologists or statisticians who are experts in their fields but not expert programmers. Yeah, so that's my initial interest. So the main thing I've done with Julia is I wrote this plugin package called Gadfly, which I'm going to talk a little bit about. Yeah, so Gadfly is sort of based on this book by Leland Wilkinson called The Grammar of Graphics. And what it is it was his attempt to look at a lot of statistical graphics that are being generated and try to decompose them into common components and build sort of a grammar out of them. So, of course, the most popular implementation of this is Hadley Wilkins' ggplot2 for R. So Wilkinson's original implementation is a Java program called Invisit. I don't think that ever became really huge. It was a proprietary software, and the licenses were like $10,000. Even though it wasn't really sophisticated visualization system, much more than anything else at the time. You also could write like a bunch of XML. Yeah, so let's jump into it. So like the simplest sort of plot you can make in Gadfly, it looks like a lot of other plotting software. You just call plots X, Y, pass some data to it, and it makes a scattered plots. So Reveal did something bizarre to these plots, and the fonts are a little bit mangled. Usually it looks a little bit better. So yeah, so this is a plot in Gadfly. This is all in iJulia notebook. Yeah, so it's outputting SVG. It's some fancy SVG, so you can. Oh, great. Well, I'll show you an IPython notebook today.
Which browser are you in?
I'm in Chrome. Okay, maybe I should just show you the notebook. This is pretty terrible.
That's usually the story with IPython implementations.
Yeah, I stopped even trying to use slide mode after a while.
Okay, I'm just going to do the notebook because.
Yeah. And if you increase the magnification, it should work pretty smoothly in Chrome.
Okay, let me try to do that. Is this good?
Yeah, perfect.
Okay, so I'll just scroll. Yeah, so it's generating SVG. It's sort of fancy SVG because it almost always works.
Something you changed a few days ago and made that happen.
I was trying to fix some other bugs. I'll show you my plots. Yeah, but really in Gadfly, this is really just shorthand. The full specification of this plot looks something like this. So it's a bunch of like scales and statistics and guides and stuff, which of course prompts the question, what is all this stuff? Yeah, so sort of the picture I have in my head of Gadfly and grammar of graphics in general is sort of like this. There's this toy that this company makes called Little Bits, and they're like these little things that you can plug together and make tiny devices with. So the idea is like kids can learn about electrical engineering without like having to use a soldering iron or worry about like shorting components out. So I think of Gadfly as sort of the same way as defining some sort of reusable components that fit together in a well-defined way and that you can build a wide variety of plots and visualizations with. Though, I mean, just like this, it's by no means like any visualization. To do that, you need a level lower. You need a soldering iron. Yeah, so components in Gadfly work sort of the same way. So this simple scatter plot, it looks something like this. It passes through several levels. So if this is the data, we bind it to what's called aesthetics in Gadfly. And aesthetics are like named variables that define the connections between the different components in the plotting system. So you know, components are sort of like functions, except a level higher because they work on named inputs and outputs, and they're applied in sort of defined order.
In this specific instance, what is a component and what is an aesthetic?
In this specific instance? Yeah. Okay, so the labels I put on edges, those are aesthetics. All these boxes, those are what I'm calling components. Yeah, so because these fit together in a defined way, all you have to do is just add new ones to the plot function, and it sort of works. Yeah, so the order that you add these things to the plot function doesn't matter. So like basically you can put the plot function in any order and you get the same plot. Yeah, so I'm going to show some more example plots. I should say I'm plotting a bunch of example data sets that are from our datasets package, which is a very nice place to get example data. It sort of collects like all the example data from all of our packages. So yeah, so this is like the famous data set measuring iris features of the species. Yeah, so if you bind new aesthetics, you get different behavior. So here, this was like the last plot, but I'm binding categorical data to the color aesthetic. Yeah, so the other important components are statistics, and statistics are sort of like you think of plots that you normally draw, like box plots or density plots. What we've tried to do is extract the actual summarization or computation out of those statistics and separate them from the drawing routines, which makes the system much more powerful. So like here's like a sort of heat map thing drawn one way. This data set is like some macroeconomic stuff of different countries over a span of 1965 to 1990. So the x-axis is GDP, or the x-axis is here, the y-axis is GDP, or actually percent change in GDP. And you're sort of drawing a heat map of what countries changed how during those years. But if you bind it a different way and use a different statistic, you get a different plot, even though it's sort of using the same geometry to draw it. So this is the same data set, but instead we're doing, so I've defined the statistics, I should say. So here I'm using the summarization statistic to accumulate how many things fall within a bin and colored that way. And if I take that statistic out, I get a different plot. So here I'm directly plotting colors that are bound to percent change.
How do you specify that, sorry?
Oh, sorry. Yeah, so this first plot, it's changing basically because I'm changing the statistic. I'm changing how the data is summarized, and also bound to aesthetics, even though I'm using the same rectangle geometry. I wonder if this works. Okay, so that sort of works. Yeah. So here's a bunch of warning messages. So one thing I should mention is that I've tried, at least with recent versions of Gadfly, to make it sort of type agnostic. So, and it's not limited to just like plotting floating point numbers like a lot of systems are. It's because we have sort of a rich type system. You can plot anything that sort of behaves like a number. So here, this iris data set, it's not annotated in any way, but I happen to know that it's centimeters. So I can use SI units to actually make unit-fold types, and I can still plot them, even though we might want to change how it's printed a little bit. So that plot's perfectly fine. And there's no special cases to handle SI units in Gadfly. It just sort of works if you define the right arithmetic operations. Yeah, so this also works mostly for time. So here's George W. Bush's approval or disapproval rating. Yeah, so these 3 lines, I'm just converting columns into time objects. And here, I've bound the x aesthetic to date and the y aesthetic to value, which is approval or disapproval. Yeah, and so it just sort of works, even though it's not primitive numbers that I'm mapping along the x-axis, but dates.
And in particular, if the dates were not evenly spaced, you would see that reflected in the plot, you're saying, right?
Right, yeah.
So if you had a gap in sampling, that will show up.
Yeah. So like, I mean, like these data points aren't specified as 2005.5. It's specified as, you know, whatever month, whatever day. Yeah, and it knows how to map those. Yeah. So more recently, I've been adding stuff like faceting. So I've sort of taken a different approach to faceting in Gadfly. Rather than introduce a whole other layer to the grammar, I've sort of tried to fit it in with the existing grammar. So the insight is that you can sort of think of facets as a geometry that's sort of recursive and draws smaller plots. So that's what I've done. I've defined a subplot grid geometry, and what it takes is another geometry, and it'll recursively call plot and draw smaller plots and work out how to align them and how to compose them in there. Right. So this is. I mean, I can show you. So unfaceted. This is like. It's too much for Chrome to handle. Yeah, so maybe I will try that again. Yeah, so faceting, I mean, it works like any other geometry, except the aesthetics here are X group and Y group, and you bind some sort of categorical values, X group or Y group, and it splits it into subplots this way. So here's one binding Y group. This is vocabulary versus years of education, and I've split it up by male versus female. Yeah, so you can bind X group and Y group at the same time and get a big grid, but I was struggling to come up with an example that actually fit on my slides, since it just sort of explodes into a gigantic array of plots. Yeah, so let's
get two plots in there.
Oh yeah, okay. So let me take this apart a little bit. So it doesn't crash. So let's do like a simple set of box plots first. Okay, so these are box plots, and on the x-axis it's years of education. I don't know what the units are on the y-axis, but some measurement of vocabulary size. Right, so that's a basic box plot. But to go one level deeper, I want to split it up by some categorical variable. So I'm going to bind y group to sex, and then do the subplot grid geometry. And it takes as a parameter the geometry that's used for those subplots. Yeah. Yeah. So you can make some pretty sophisticated arrays of plots that way.
Is there control over the text, like vocabulary by sex? Could you make that say something different?
Yes. This will maybe work. Oh, what's this guy?
I make that mistake every time.
Yeah, I wonder about that distinction if it's not. It's not work. Yeah, so changes the goals.
Really slick. I wanted this in other plotting environments forever. Good faceting.
Yeah, it's not perfect yet in Gadfly. You can still like use some issues, but it's improved a lot.
Do you have control over the relative sizes of them, or are they all kind of the same? Like, could you make one of them twice as big or twice as tall as the second?
I think there's some. I don't have very good support for that yet, but I at least have the mechanism now where I can which I'll talk about in a bit. So I have a little bit of support for not constraining the axis to be the same. So let me talk a little bit about the back end stuff. there's a few different packages that are involved. One of them is color.jl, which is it's become one of my favorites because it's a lot of immutable types and a lot of good use of multiple dispatch. I started this, and I sort of got to the point where people that actually know stuff about color imagery, like implemented some really cool, obscure stuff that I'd never heard of. So it sort of reached a point where, as far as I can tell, it's the most complete color package in any language. I may be wrong, and I'd really like to know if I was wrong, because I can steal features from that library. So yeah, so there's a lot to talk about with this library, but I'll just touch on a few things that are useful for visualization. One of them is perceptually uniform color spaces. So what this is our perception of color. We're not like neutral observers of color. We have particular frequency response curves. And you can plot this here, since we have this data in the color package, of course. So of course there's three sorts of photoreceptors in our eyes: long, medium, and short. They're labeled usually, and they have sort of this x-axis is wavelength in nanometers, and they have this particular response curve.
Are those negative numbers?
Yeah.
That can be right.
Yeah, I don't know.
It's the particular basis for this color spaces. It's defined as well.
Okay. Yeah.
Wait, what?
Yeah. It's just a basis function. The neural models.
But it's supposed to be the empirical response curve too.
No. The one that works is XYZ. That's the actual color reception. This is the LMS color space.
Yeah.
Okay, so I should slide this on XYZ. Yeah, so there's like tons of convert methods in colors. One of the main things, so you can pretty much convert between any pair of color spaces. And there's like, I don't know how many color spaces we have now.
You got 2 Ys. Yeah.
Well, yeah, it should be Z.
And
The third one.
Audience length.
Oh, so maybe this is the right one, yeah. Okay. Yeah.
No, man.
Okay. Right, so yeah, like humans have better color vision better color vision than most mammals, but it's mostly because we started eating fruit and needed to tell what fruit was right. So it's not really good at like mapping data to that. Yeah, so we have a few perceptually uniform color spaces implemented. Here, so let me show you a comparison. So this is HSL, which is like the common one that's implemented in SVG and HTML and CSS and like every graphics program. This is lab color, which is one of the standard perceptually uniform color spaces that was standardized in 1976.
What does perceptually uniform mean?
Oh yeah, so let me explain. So they both have a hue parameter, and I'm varying it by constant steps. So this isn't the highest quality color reproduction. You can hopefully see that like in this you have some like very obvious gradations, yet when you get into this green period, like you sort of can't tell the difference between them. Whereas lab, like the hue parameter maps much more closely to what our perception of hue is. So this looks to us like more continuous steps.
So the uniformity there is in like least noticeable difference, kind of like it's like the colors are like more densely packed in places where we can better perceive the differences.
Right. Yeah. And further away where you can get less perceived differences. And the same thing's true. They both have sort of a lightness parameter, which I mapped on the y-axis. But if you look at like HSL, like this like doesn't really look the same lightness as this, at least not to me. You know, it's the same lightness parameter.
You can get a little more screen real estate if you go to the view menu and hide toggle header or toggle toolbar. Okay, there you go.
You can also the presentation mode in Chrome. That helps.
Okay.
That helps. In the view. The presentation.
Okay. Yeah, so we have a variety of perceptually uniform colors. And this is a good way of generating, if you want to actually map data to hue, this is a good way of doing it. The other way you want to map data to colors is sort of in a categorical way. So a lot of packages that even do have a somewhat sophisticated notion of color and use this more sophisticated color spaces don't do it in a very good way. So for categorical values, they'll just pick evenly spaced hues but keep the other parameters the same. Just sort of not really the problem that you want to solve. But luckily we have a better solution, I think. So we actually have an algorithm in colors that will choose a set of maximally distinguishable colors. And this is something that Tim Coley did and helped me port to Julia. So yeah, so you can give it a bunch of choices of the different parameters, and then ask for, in this case, 10 colors, and it's going to generate 10 colors that are maximally distinguishable. And we actually have a wide array of color difference formulas implemented, so we can do this pretty well.
So the Daniel's version is about 100 times more sophisticated and tunable than anything I've ever looked at.
So I think like one of the main things we added was so a lot of plotting packages they choose their colors without regard to color blindness, which is a pretty significant proportion of the population, especially the male population. So I don't know what it is, like 5 to 10%. Yeah, so deuteranopia, that's the most common form. But we've implemented a simple simulation of that. So we can optimize the distinguishability of these colors after transforming them into this sort of reduced skin. So yeah, so if you simulate color blindness and do some colors, you get a different set. So yeah, so this looks different from this primarily because like these are terrible choices if you're red-green colorblind, and it avoids those choices and it chooses a lot of yellows and blues and browns and things that you can't distinguish. Yeah.
Do you have a distinguishable colors function that like has still distinguishable colors when somebody prints out your color plot on a grayscale printer? Because I had this very nice paper with a Gadfly plot, and somebody printed it out.
You can pass in a set of seed colors that what it effectively does is load the queue with those colors at the beginning, and then all future colors will be chosen to be maximally distinguishable from those. So if you basically choose the paper background as one of your seed colors, and if I remember correctly, there's no limit on how many seed colors you ask to basically avoid. It will then it doesn't avoid those any more than it avoids nearby overlaps between any other pair of the groups. They're not special in any sense. But
you could also maybe do that by picking colors with very different lightness, using a different color space, maybe.
Yeah, something I just like. I mean, I like my colors in my PDFs, but then people tend to print them out, which is a waste of paper. But they do anything.
What's the advantage of making both grayscale and fiction?
Yeah, you could do that. I mean, transform is an arbitrary function that takes the color map to another color. So I mean,
yeah, grayscale prediction would be awesome.
It would be interesting to use jump to try to anything is possible.
I mean, and the version that Daniel wrote, I mean, you already can actually choose a range of, with hue saturation value, I think, are the 3 parameters, right? So you can specify that all the colors should be within some band of hue or something like that, right?
Yeah, so I mean, like all those parameters you can limit to some set.
Right.
Gadfly it's implemented. I wrote a graphics layer which I use to implement Gadfly. It's called Compose. I'll talk a little bit about that since that'd be pretty important to how Gadfly is implemented. So what is it? It's sort of a declarative graphics system, which is a level higher than sort of like the logo, set in the turtle, circle sort of drawing systems. And it's basically based on trees. I won't go too much into depth to it, but like here's a really simple example. The tree is specified where every internal node is of type context, and then the leaf nodes that hang off of it are either like shapes that you're drawing or properties that modify the subtree of that node. So here, I have a root node here. I'm applying stroke that affects the whole tree, and then I have 2 subtrees here, which draw 2 circles of different colors. And it's based around a compose function is what I call it, which is basically make a tree out of something that's vaguely like an S expression. So a lot of the drawing code and Gadfly is like big S expressions, and then you can compose on it.
How is that specifying that the circles should overlap? I don't understand.
Oh, so this is I have 2 circles. If you don't assign units to this is like a 3rd way across. screen. This is like 2/3 way across the screen, and then the radius is like here.
Okay.
It's like ticks.
Maybe a little bit, yeah. Yeah.
Is there a way to change the plotting coordinate system, or is it always 0, 1, 0, 1?
Oh no, you can change this. Yeah, and that's sort of the main. One of the main things it's designed to do is to take into account all the changes in coordinate systems that you have to do drawing sort of complex figures. Yeah, so here's another example. This is a principal triangle. So yeah, so it's not very many lines of code. It's not hard to draw this in any drawing system, but I think it illustrates nicely what I mean when I refer to it as a declarative drawing system. Because like a regular function that you use to draw a Sierpinski triangle, it's got this recursive call, but it's going to call it 3 different times to do 3 sections of the Sierpinski triangle. But if you notice here, I'm only calling it once, and I'm just sort of recontextualizing what I get out of that one call. So here it's actually not a tree. I'm building a graph. So it's only ever making one triangle and just like putting it in different contexts. So when you go to draw this, it just does a depth first traversal of that graph, and it runs into that triangle a bunch of times in different contexts, and it draws it in different places.
Do small changes to one of the numbers make it really funky?
Oh. Yeah, so and one of the problems that it's designed to try to help with is these coordinate system changes. The other one is that in like actual figures and graphs that you're drawing, you have to mix coordinates a lot. If you're dealing with text especially, there's a lot of things that are specified in absolute coordinates and a lot of things that are in relative coordinates. So there's a pretty sophisticated notion of units in Compose. So W means half the width of the parent context. Whereas I also have 1 centimeter here, which means 1 centimeter. So here I'm drawing the same composed graphic at different sizes, but this circle is specified in absolute coordinates, so it stays the same size, whereas the outer one is relative coordinates, so it expands. Yeah.
So does it have a built-in idea of the paper size or something, or like what does a centimeter mean? Like it's on a projector right now.
So SVG has a notion of
I see here.
Yeah. So the bigger question is, what does a pixel mean? I think, and I'm sort of like scaling by some common value there. Yeah, so I can write to SVG, PostScript, PDF, PNG. PostScript, PDF, and PNG I'm doing through Cairo. I'm generating my own SVG, which has a number of benefits. One of the most immediate ones is that I'm much more efficient at generating SVG than Cairo is. So here I'm drawing the same plot, one using Cairo as the backend, one using my own SVG generator. So you can see uncompressed, it's like 1/3 of the size, and compressed, it's like half the size. And this is just because like Cairo's not necessarily bad at SVG, it's just a very low-level system, and SVG is a high-level system. It's sort of this fundamental inefficiency from jumping from low level to high level. It's got to repeat a lot of stuff because it doesn't know the larger context.
Is it also better performing?
Performance?
In terms of text generation?
I haven't done a ton of work optimizing it yet, so it's probably not as fast as drawing this kind of things. Although with SVG, if you put a ton of geometry into it, it's more like how fast the browser can draw. How fast you can do it. Yeah, so the other cool thing about generating your own SVG is you can sort of exploit some obscure features of SVG. So one of the things I have in Compose is you can actually embed JavaScript in SVG. So here's a really simple example. So I have a JS call property, and you can just like stick some JavaScript in there, and it's going to assign a unique ID to whatever this turns into in the generated SVG. Call that JavaScript property. So here it's just a function that transitions to a random caller that recursively calls itself. So if you click on it, it creates this hypnotic display. Yeah, so obviously you don't want to write a ton of JavaScript in these strings like this, but it's really useful if you want to hook up JavaScript event handlers. So like when you click this thing, I want to call this JavaScript function, I need to find something else. And that's what I use to implement panning and zoom. Yeah. Another big advantage of sticking everything in the SVG, which is what it is by default, is it's super easy to include these interactive plots in your website by just using an object tag instead of an image tag. You can still use an image tag with SVGs, it just won't be dynamic. So there's that nice fallback if JavaScript is disabled. Yeah, so the next thing I'm going to talk about is stuff that I've merged in the last couple of weeks regarding layout. So one of the things that's frustrated me in the past with plotting libraries is that they have a very rigid notion of how things are laid out. And this is despite having a pretty long history of layout problems being researched and practical solutions. So obviously we've had tech for a long time, we've had browsers for quite a long time, and they've become very sophisticated in their notion of layout. So you can have alternate layouts if you're looking at it on the phone versus the larger screen. So also operating systems are starting to integrate like these constraint-based systems where you can do very sophisticated layouts and dialog boxes. So plotting libraries are like, if you shrink the size of the plot, it's just going to like overlap little labels and it's just going to look like garbage, and it doesn't even know what it's doing because it's not smart enough. So I'm starting to try to fix this with Gadfly, I hope. So the particular way I tried to formulate this as an optimization problem is like this. And so I realized part of the trade-off with layout is you don't want to do anything that's really unintuitive. Like you don't want like to resize it and have things totally rearranged. What you really want to do is simple things like word wrapping and having things moved into new columns. So everything is pretty much laid out in a table, except each thing in the table might have multiple different ways you could lay it out. And what I'm trying to do is, if this is the plot here, and this is like labels and color keys and stuff, there's going to be multiple ways of laying out the color key. What I want to do is try to find a set of layouts for each of these cells where nothing's overlapping, so it's a feasible solution that I'm maximizing the size of the plot. So I've implemented this in Compose using it's a table system. It's easy to formulate this as a mixed integer program, which I'm solving with Jump. If you have Jump installed, but I also have a backup brute force solver, which is it's totally adequate for plots because there's usually just like a dozen or 20 combinations that you have to iterate through. But you should, if you have Jump installed, you should be able to solve larger layout problems. So the main thing this does so far is so this is the same plot. I'm just drawing it at different sizes. If you shrink it, it figures out, to make a feasible solution, I have to wrap this over here. And because you're trying to maximize this, it knows I'm not going to wrap it to 3 columns because I don't have to. And I want to maximize the size of the graphic. So it also...
that'll save me about 500 hours over the next
So what I've implemented now is like wrapping keys to new columns, rotating. These labels will rotate if you shrink them enough. That sort of thing.
Is it crazy to imagine a system that would allow you to, as a user, do like what PowerPoint lets me do, which is kind of just mouse over and make things bigger and smaller to make it just the way I want it to?
It's conceivable. I think it's definitely possible. Yeah, it just depends like what the best interface is.
I wanted to just guess the right thing the first time. I don't want to ask myself, this is perfect. You did the right thing.
If I believed that that's always doable, I would not have asked my question.
I know.
So I mean, realistically, no matter how good it is, you sometimes have to edit the graphics, which was like part of the motivation for making my own SVG generators, because it generates really clean, simple SVG that you can even edit in an editor, unlike the stuff you get from Cairo, which is just like a gigantic mess. So now that I have this solver, it also, I mean, it has a new level of insight, the plotting function, because you can still shrink it so small that it can't draw it, but now it knows that it can't draw it, and it's going to give you a warning. Yeah, so it's going to output garbage and say, look, I can't draw this correctly. There's no feasible solution. Yeah, so the other layout problem, which is demands some different methods, is label layout. So you can ignore all this code. I was just drawing a little diagram. Well, my diagram to complete now. Yeah, so I mean, the basic problem is you have these points and you like to assign labels to them. But you need to position these labels so optionally they're not overlapping. So like, I mean, like most of these interesting layout problems are NP hard, but yet there's usually a solution that's pretty good. So this is no exception. And sort of the pretty standard way of solving this is through simulated annealing, which again, so you get pretty good label placement. And the default behavior is if they can't figure out how to place a label without overlap, it's just going to hide it. But there's a penalty in the optimization function for hiding the label, like a pretty big penalty, but not as big as overlap. So, yeah, so like this plot is mammals' brain size versus body size to show that humans aren't that exceptional.
Can you do that same thing for lines? So rather than having legends, you have that.
I don't know that yet. Yeah, so the label layout, it only sort of knows about points and labels. So I don't have it yet.
Because like, yeah, my next somebody does that. So I always end up wanting to speak with it.
Yeah, I really like to do that.
If you zoom in, will more labels show up there?
I don't have that implemented yet. I'm going to do that soon. But of course, I broke the Zoom function. At least the labels and the lines.
So which way makes humans' brains better?
We've all seen this work for real, so yeah, we know it works.
Yeah, so that's basically Gadfly and Compose. The last thing I was going to show. Yeah, so along with this being the first JuliaCon, this is the first year Julia has participated in Google Summer of Code. And there's some really good stuff going on. I wanted to show a little bit of React. So one of the students is working on this system called React, Shashi Agabda. And GSOC's only halfway through, but he's made really amazing progress with it so far. So you can do some cool stuff. So what it is, it's a general purpose signals library it's based on the Elm programming language. And functional reactive programming is the paradigm. And this interfaces very nicely with a system that's added to Python recently, their widget system, which sort of allows you to display widgets and have bidirectional communication between that widget and the Julia process. So here's R is a simple signal that's assigned an initial value of 1. XS is just an array of 10 random numbers. And now I'm going to lift a function into a signal. So what this does is I have a simple anonymous function here. I've sort of overloaded R a little bit, but and I'm attaching it to this R signal and attaching some computation to that. So now I can update this R signal with a push function. It should, even though this wants to scroll way down for some reason, this array is updating as it's being raised to a higher power. It does that automatically. So that's kind of cool, but you can do more sophisticated things. Yeah, so one of my favorite sorts of plots is hexbin plots, because it's, I see a lot of plots that are point clouds where there's so much overplotting that I don't know what's going on. So hexbins are like a really good remedy for this. It's unfortunately not implemented in a lot of libraries, but I do have it in Gadfly. Yeah, but the one complication of hexbin plots over point plots or scatter plots is that I have to choose a bin size now. So fortunately with IPython widgets and this React framework, I can sort of tinker with the bin sizes interactively. So I've created this slider signal, 2 slider signals for X bin count and Y bin count. And I've used lift to turn the plot function into a signal and connect it to those 2 bin count signals. So now I should be able to change this, and it's going to increase the bin count to each odds. Yeah, so that's pretty satisfying because it works with no special support from Gadfly. It's it's a well-designed general purpose system, and you can sort of do a lot of stuff like this one.
Do you have any guess about what the major source of latency is here?
Yeah, so I mean, it takes a little while to rejob, partially because this is like a data, it's a fairly large data set, like 20, 30,000 points in it. But also because I put like zero effort into optimizing any of this. So I think it could be a lot faster.
But with smaller data sets that can plot pretty quickly, is it like fairly interactive if you drag it around?
Yeah, I think so. I wonder if we could, we should try to do this.
Try like plotting a sine function.
Oh,
Just simple.
Make it depend on that's an arbitrary way.
Yeah. Yes.
You'd have to signal on that one.
Let's just change in the range across this body. It's still not very fast. I think it's evaluating at a lot of points. I'm not really sure. But yeah, like I said, I cannot profile this problem. Yeah, but you can sort of hook this up in arbitrary ways. There's still a lot of work to be done to make it usable, but it's pretty handy. Oh yeah, so the last demo I was going to show you. This is not limited to hooking up plots to sliders, even though that's really useful. Can we turn these lights on? This might look better.
You're going to lights down more?
No, on.
Oh, on.
It's on the screen in front of you.
Oh, great. On the.
Yeah, so I was trying to come up with a general purpose demo of this React system. And what we thought of was, why don't we try to implement a theremin in Julia? So if you don't know the theremin, theremin was like a mad scientist, Russian engineer, inventor, and he came up with this musical instrument that was unique in that you don't touch it. It's just antennas, and how close your hands are to it changes the pitch and volume. So what I'm doing here is MacBooks have an ambient light sensor that I use to blur the screen the lighting. So I have a little C function here where I'm reading that value, and I'm using Shashi's system to lift that into a signal. Now I'm using audio I/O, which is meter.5 minutes, to play a sine wave and varying that based on what the light sensor is. So,
all in 4 lines of code.
Theremin's notoriously hard to play. There's only a few people who are really good at
Code a lot bigger?
What's that?
Nathan just needs to code a lot bigger?
Oh, yeah.
Is that code in a gist somewhere?
Not yet. I could do that pretty easy. Yeah, so it's you also have to there's a little bit of C code here to read that signal, and it's OSX specific. Yeah, that's React and Gadfly composing color. So it's supposed to be.
Questions?
Yeah, I was curious if you have like an arbitrary objective function for that layout optimization, or just in the example you were trying to maximize the size of the graphic, but I was wondering if you could have a penalty for a word graph versus like relative to the value of an extra pixel in your graph and so forth.
Yeah, to some extent, yeah. So I didn't talk about like the general mechanism I'm using to implement this. So I said compose was like a system where you're specifying a tree and then it's drawing it. So the way I'm doing this is you have to know the absolute size of what you're drawing it to do this. So I'm using part of the tree is not materialized until draw time. So I introduced the notion of like a context promise. So it starts drawing it and then gets to that point and then decides what to do. So you can implement like any sort of layout system using that mechanism. So like this label layout is a totally different optimization. It's using the same thing.
One of the things that I've never understood that I'm sure you can help me understand is so I'm starting to get it's like you have the different aesthetics, which is kind of like different properties of your graphic that you can then map to different varying values in your data set. Basically, you're kind of like linking those things together, right?
Yeah.
And so that part kind of makes sense. But then there's always like the last argument in the plot. It's kind of this freestanding geom dot line or whatever sort of argument. How does that? I mean, it kind of it sort of makes sense that like I just replace that with the type of plot that I want to draw, sort of, and like some of them I can put more. I can sort of stack up multiple of them. What's the kind of conceptual underpinning that like helps make that part of it make sense, and I don't just feel I'm like replacing something without anything.
So you're particularly talking about like stacking up multiple geometries, or just like how does geometry?
Well, I guess like why is it that that's not a like geometry isn't an aesthetic that you're like mapping a constant value to, or like I get that I'm kind of just trying to figure out how it fits into, and like what the other ones are all keyword arguments, and that one is not a keyword argument.
Yeah.
And I feel like there's probably like a really clean conceptual reason why that would be that way.
So conceptually, I'll say that the aesthetics are representation of data, and the components like the guides and the geometries and stuff are all at some level functions that operate on the data.
Okay.
So like geometries and guides are always like the terminal function that actually draws something, but then you have scales and statistics which alter the data in some way. So it's sort of this pipeline where the data gets scaled and it gets transformed by a statistic and it gets drawn by the geometry, but it's all operating.
And can you always put multiple geometries kind of arbitrarily, or?
Yeah, so it's not obvious, but what it's doing when you put multiple geometries is creating multiple layers. So there's a notion of a layer, and a layer is just something that has its own statistic and its own, potentially its own data and its own geometry. So you can put as many as you want, and you can have different data layers too.
So just a question about so is there a way to compute statistics externally? So often, they're the most computationally intensive bit, and you might want to use it against something else.
Oh yeah, that's a good question. There's not a good way of doing it right now. So like I have a density statistic to do density plots, but it's a custom wrapper thing. So I think the solution, it should be easier to make sort of ad hoc statistics. That would be the best thing.
And to extend as well, if you're building some sort of model class, you want to be able to output.
Yeah, definitely.
There seems to be a question though of at what point should the statistic be really in the plot as opposed to a separate statistic step in your computation?
Yeah.
For box plots, we needed that, and Daniel added it in. For box plots, now you can specify all the points, all the 5 points of the box plot externally.
Right, yeah, so by default it would force box plot statistic in it, which would just take X and Y and compute a bunch of values like upper fence and hinge and middle point. And of course with box plots there's multiple ways you can do a box plot. There's like one that's most common.
Do people ever ask for 3D graphics like the Satinsky sponge?
Yeah, people ask for 3D graphics. They don't realize like how big of a project that is.
I'm already scared of it.
Yeah. Yeah, so the difficulty with 3D graphics is like everything in the back end is different. So it'd be great to have a 3D graphic system where it has a similar front end, but unfortunately I doubt there's much that you can do.
I mean, it seems to me that the real strength of Gadfly, compose and color obviously are more generic, but the real strength of Gadfly is that it's presentation of data. And I've always found that presentation of if you try to do a 3-dimensional version of a 2-dimensional plot, it just comes out awful. I mean, the kind of stuff that Tim does, where you're visualizing things in 3 dimensions, but there's no axis on it, is very different.
Yeah, that's something Nash is doing. It's good for that.
Right, exactly.
All right, thanks, Daniel.